Welcome to Pratidwani, where we try to humanize science. I am your host, GV Pawan Kumar. It is my delight and pleasure to introduce you to my dear friend and colleague, Srijit GJ. Srijit is a condensed matter theorist and also an associate professor at the Department of Physics, Indian Institute of Science Education and Research, Pune. He does some very fascinating research, which includes quantum many body systems, and he utilizes statistical mechanics and critical phenomena and various different allied research areas and methods to unveil some fascinating properties of quantum Hall effect and uh, various different spin systems and also the very interesting strongly correlated systems and many different kind of quantum condensed matter systems. And he of course uses a lot of interesting computational and semi-analytical methods to attack these kind of problems. Welcome to Pratidwani, Srijit.
Thanks, Pawan. Yeah.
So, Srijit, I know that you have a very kind of interesting and very strong background in physics, but I want to know how did you get interested in science, and what is the kind of upbringing you had? Could you just let us know a little bit about that?
I think I always wanted to do science. I wanted to be a scientist, but physics was not the thing that I thought I would be working on. I in school I liked chemistry. I liked doing experiments at home. So when you're in school, you read about stories about scientists, and most of those stories are about scientists mixing things in test tubes and stuff. And that's the picture of scientist I had. And so I enjoyed trying to do some of these at home. I liked mixing stuff I found at home and playing with this. My mother used to buy these hydrogen peroxide things to clean.
Where were you born, by the way? Where were you?
I grew up in Trivandrum.
Trivandrum. Okay.
Yeah, so I liked putting hydrogen peroxide on random stuff and seeing it oxidize. My father was a hobby, had a electronics hobby. He was a government servant, but he had a strong interest in doing electronics, and so he had these transformers and step down devices for powering DC circuits. So I used to take those and try to hydrolyze water. Electrolyte split water. So it was fun. I liked doing chemistry experiments. But as I learned more about chemistry, somehow the actual chemistry was different from the picture of chemistry I had in mind. So then I got more interested in other stuff. For a period, I was interested in aerodynamics. I went to some kind of training or some kind of summer class on some kind of aero modeling. There was a government institution in Trivandrum called Jawahar Balabhavan. So I joined for some classes there in one of the summer, and we had an aero modeling class. So I went to the first class, but unfortunately, the instructor there got some other job and he left. So I didn't learn any aerodynamics, but the introduction that he gave to aerodynamics and design of aerofoils, I was very fascinated. So for a long time, I tried to sort of do some design at home with whatever things I had, some motors that were left from my father's electronics hobby. And then I tried to make fans with paper and cardboard and smoothing it with candle wax and things like that.
Nice.
So that fascination fizzled out as I figured out that it's very difficult. And then I was fascinated by mathematics for a while because my teachers told me that I was good at mathematics, or relatively good at mathematics. So then for a while I liked reading math books. And then at some point I had a fantastic biology teacher. So I thought I'll do biology in high school. And so I thought I did fairly well in biology. So I thought I'll become a doctor.
Uh-huh.
I even joined medical school.
Oh, did you? Wow. Okay. Okay.
And then after a week, I sort of had a panic attack. And then I finally decided to join an engineering school. So, yeah, I had a cold feet after a week, and then I ended up joining an engineering school. I did mechanical engineering.
Okay. Yeah, I will come to that because I can see that you also have interest in slightly applied problems because I've discussed in the past, very kind of in a passing way, and you did mention about some devices and other interesting things. So this development has been very interesting, Srijit, because I know that you have excellent knowledge of physics and mathematics. I mean, it's related to the physics what you are interested in. Uh, Growing up in Trivandrum, how was it? Like, did you have kind of somebody who was already kind of motivating you to get into research, or this has all happened kind of organically?
No, there was nobody. My family did not. I mean, I think the best thing was that there was absolutely nothing to do during summer. And I think boredom was the best thing that happened. So I had a lot of free time during summer. I read a lot. Well, not as much as some of the other people I know now, but I still read a lot. And I tried to do experiments at home. So I think that was fun. Most of it was boring and led to nothing, but still, I think that was the nicest thing about being in a small town, relatively small town at that time.
But Trivandrum also has a bit of kind of colonial outlook, right? Because if you see, especially the buildings and other things,
It's a large administrative center.
Yeah,
Slowly changing, but yeah. Other than yeah, I did have a lot of books to read. My grandfather had bought a lot of books. He worked in the Kerala University. My mother worked in the Kerala University, and my father had a lot of interest in electronics, as I said before. So he had a lot of books on electronics. So I read many of them, or to the extent I could understand. And there were my cousins who were doing bachelor's degree at that time, and they had a lot of books. I still remember this book called Teach Yourself Calculus that my cousin used to study, and I remember reading those. So there was nobody I would say was a mentor or anything, but there were a lot of things that helped sort of get me into
into
science.
science. Yeah, fascinating. Was it also a time and place where you had a lot of friends?
Yeah. So I lived in a part of the town where there were a lot of coaching institutes, not coaching institutes, but tutor. And there were a lot of my classmates who used to go to those tutoring places, and they all used to pass in front of my house. So they all would leave for the classes an hour early, and they would come to my house and we play cricket. And then they would go to the classes. I somehow didn't join any of them, but joined the tuition classes. But I had a lot of friends to play cricket with because of this, because they would all come to their tuition classes early enough, and then we would play for 1.5 hours in the evening. And and one batch goes and the next batch comes and then I play with them.
So you're the kind of constant person to play cricket with them, is it?
Yeah, so that was fun. So yeah, I had a lot of friends. We used to play cricket, but I don't think we did much. I mean, Trivandrum was a small town. It's not like how it is now, where you have a lot of things to do outside. We played cricket, we chatted a little bit. That's it. Yeah.
One of the unique aspect is that you quit medical sciences to join an IIT.
Yeah.
Is that right?
Yes.
So
I have to admit I signed up. I mean so I had cleared some exam to be able to join medical school, Trivandrum Medical College. So I filled up the form, joined the program. Then about a week later, I got admission in IIT. Then I had
IIT Madras.
IIT Madras. And then I wasn't sure what I wanted to do. My parents never forced me to do anything in particular, but they did wish that I continued in medical, continued to be doing medical sciences. But since I had no idea, and my parents also had limited knowledge about this, so actually my mother took me to this doctor, practicing doctor in medical college. His name is Dallas. He he told me that you were probably thinking of being a doctor as a charitable thing to do, but actually it's just a work. So daily these are the kind of things they do, and this is how you think about it. And he sort of discouraged me.
He was a medical doctor himself.
Yes. No, I don't think he would discourage, but the way he presented it, it was more pragmatic. And then I realized that being in IIT is probably an easier path than being a doctor. So I ended up going to. I wanted to do physics at IIT, but I wasn't really sure about career prospects after physics. So I ended up, and my parents also was not. They were not sure what one does after doing physics. So we decided that I'll join mechanical engineering course in IIT. But having said that, I should say that when I joined mechanical engineering, I had no idea what it was. I thought it was something to do with repairing cars and something like that, but something better than that. But I don't think I understood what exactly it was.
So tell us about the transition, because as you mentioned that you were going from a conventional education where probably you were already at a kind of a level where you are better than your average class members. Was that the thing, or were you kind of an outlier already, a brilliant student and things like that?
No, I was good. I was not the topper in the class, but I somehow felt that I was comparatively better at physics and mathematics in the class, but that didn't translate to being the topper in the class. Somehow, I think I struggled a bit with languages. I that in the hindsight, the kind of things that were taught in English classes in high school, they were extremely interesting things. A lot of philosophy, a lot of things that I appreciate now, but I didn't appreciate at that time. And I thought that these things were boring. And I had a fantastic English teacher. But she sort of understood why students don't like it, because the kind of things that are taught in English in high school, I don't think I appreciated the actual meaning, beyond just the language. The stories had deeper meanings that I understand now, but I don't think I appreciated when I was in high school. So I don't think I paid much attention to learning English and stuff. So I did not do well overall. I mean, I won't say I didn't do well, but I was never close to being even the topper anything. I did well in physics and math. That's all.
Very fascinating, because this is something I also feel uh, when you revisit a lot of stuff what you've studied, including physics, by the way. Uh, as let's say a person who is not preparing oneself for an examination, but just reading to understand or to even just explore, then the pleasure of exploration becomes much more, right?
That is true.
Yeah, and I find it, especially studying physics now. Uh, of course, you will do it also as part of your research, but there are certain topics which you may not even use it in your research. But the fact that you would have studied in the past and you revisit that suddenly gives you a different context and different
That is
point. Yeah. So I just want to kind of double click on this transition where you are now going to IIT Madras as a mechanical engineering student. Tell us about how does that transition happen, and what is the kind of stuff what you studied there, and
I did a regular mechanical engineering course. I did a dual degree, which meant that I did about 3.5 years of standard mechanical engineering courses and 1.5 years of master's level courses, and I did about a year and a half, I think, about of master's thesis project. So first 3.5 years we had standard mechanical engineering courses. We had material science, we had design of machines, hydrodynamics, fluid mechanics, and during my masters I mostly worked on fluid mechanics, combustion engineering, design of IC engines, and those kind of stuff, heat exchangers, refrigerators, those kind of things. And then I did a master's thesis doing experiments on supersonic flows, acoustics from supersonic flows. So
you used Sinclair method, right?
I did. So that's the highlight of my master's thesis. So we had a. So at that time, probably it wasn't. Maybe it was common, but I didn't have a broad enough viewpoint. But we had we basically did experiments in a soundproof chamber where we had a high speed supersonic flow impinging on some kind of a cavity, and when this happens, there is a shock formed at the entrance, and I was studying the acoustics of coming from the vibrations of the shock, and it had a particular profile, in which directions the acoustic, the waves are stronger. So we were trying to see if these strong, it produced acoustic waves in the ultrasonic region. So we were trying to see if we could use it for combustion of fuel. My knowledge is a bit limited and also a little rusty, but we didn't actually try doing combustion, but we were trying to see how much energy is emitted in various directions and how to optimize the energy coming out of the vibrating shock. So we cannot see the shock, but my thesis supervisor, Srinivasan, he at around that time bought a high-speed camera. But even with the high-speed camera, you cannot see the shock. And then I found some reference to something called Schlieren shadowgraph. So I took the initiative to implement that. So with that, we could actually visualize the shock, and we could see beautiful, shock. I think it's called Mach diamond. It's kind of a diamond-shaped thing that comes out of supersonic flow. So if you look at the tail of supersonic jet, you see these diamond-shaped things. You could see that in the Schlieren shadowgraph, and because we had a high-speed camera, we could see the oscillations of the shock also in great detail. So that I was quite excited about it. It was fun. Yeah. Anyway, so that's what I did during my master's.
Masters. That is fascinating, and even more fascinating is the next step you took. You made a transition from mechanical engineering to theoretical physics.
Yes.
How and why did that happen? Could you just give us a gist?
Like even when I joined IIT, I had thought that I would. I mean, I thought that I would do physics, but then for practical reasons, I ended up doing mechanical engineering. But after I went to IIT Madras, I had a lot of nice physics teachers. Some of them, or most of them, are still in IIT Madras. Suresh, Arul, and many others. And I was quite intrigued, or I felt more confident about doing physics after I attended some of their classes, and they were especially encouraging me to try doing physics. So at the end, when I was finishing my master's, and so as I said, I did fluid mechanics and during my master's, and it's many of the things are very close to physics. Then, well, of course, it's engineering, but you learn a lot of physics while doing fluid mechanics. So I thought that I like physics more than actual engineering, but that probably was lack of proper information. But still, I enjoyed the physics part of it. So Suresh especially encouraged me to apply for a PhD in physics. So I finally did that. So I had two things in mind: either apply for PhD in some pure fluid mechanics type topics, or continue or move to physics. So finally, I decided to do physics.
Fabulous, fabulous. Was it a welcoming kind of a situation for you when you were applying, because you already had a background in engineering?
That is correct. I did take a risk and probably undersold myself a little bit because, I had a reasonably good resume in engineering, so I could have probably gone to a fancier graduate school with if I continued in engineering. But when I moved to physics, it was completely new. I had zero credentials, so I did take a risk there, but it was fine.
It was fine.
Yeah.
That's a very fascinating transition, Srijit, because it's not trivial to make a transition, not only just in terms of conceptual understanding, but a leap of kind of faith, so to speak.
Yeah.
Because you really have to make your thinking slightly more abstract from a very practical topic like mechanical engineering.
Well, at IIT we had fantastic courses in linear algebra. Obviously, you do need linear algebra to do engineering. I had very good courses in control systems, but when you do control systems, a good part of it is just understanding complex analysis. So that was covered. I learned quantum mechanics by reading books, and then I learned electrodynamics by watching Walter Lewin's lectures. So I don't think I had, and also I attended some of the classes in quantum mechanics in IIT Madras. So Suresh had fantastic courses on classical field theory, and so I did familiarize with many things. So it was not a huge jump, I would say, but yeah.
By the way, Suresh has appeared on the Pratibani in the past. Fantastic. He also is a great runner, marathon runner. Yes. Fabulous. It was one of the very fascinating episodes we had. That is also, before we really move forward, I just want to get a glimpse of your experience of IIT Madras, because I can clearly see that the influence of physics was equally large vis-a-vis mechanical engineering, which is also a very good thing, right? Because it's a kind of an open system which will encourage you to take something.
True. Yeah. That is true, and I should it was partly positive and partly negative. I would say that I couldn't see. I mean, it's very easy to see what physics does. You know, it gives you an explanation of the universe or world and things. It gives you an explanation of things you see around. But mechanical engineering, the way it may be that I didn't get it, but the way it's taught, it is taught at an academic level. But engineering has a huge, now I look at things and I see buildings being designed or huge equipments. I know more about engine. I have a car. So I see mechanical engineering more closely, applications more closely. I see at that time had never seen a aeroplane, but now I've seen many airplanes. I've traveled in airplanes. So I had no exposure. I won't say no exposure, but not enough exposure to see how impactful, how useful engineering is. Obviously, engineering is useful, but not, it didn't appear as cool to me at that time as it appears to me now. So I would say I may have undervalued my knowledge in mechanical engineering. So, but you're correct that it is, IIT Madras did allow me to explore other things. Yes.
Fabulous. So tell us about the transition from mechanical engineering to theoretical physics. Where did you go and how did that happen?
I was not very confident about applying in physics, so I applied to a few places. I thought that I will not get admissions anywhere, so I thought I'll do some research for a year and continue applying next year. But turns out that I got admission somewhere, so I went to Penn State. I joined this. I had applied for PhD in cosmology. I joined this research group working on loop quantum gravity in Penn State. So I worked on it for about 1.5 years.
Oh, did you? Okay, yes. I didn't know this.
And then I realized that, well, I have to think about getting a job. And students who were graduating out of loop quantum gravity were not exactly getting research level jobs. Many of them are going on to teaching. And I wasn't sure if that is what I want. I actually wanted to do research in. So I ended up, I did some research. I mean, I was in the process of learning some stuff. I was doing something called polymer quantum mechanics. It has nothing to do with polymers, but after about 1.5 years, I decided that maybe I should do something else. I was very discouraged by the job prospects. So I thought, okay, obviously, if I'm worried about job, I should be doing solid state physics or condensed matter physics. So I dabbled a little bit with doing condensed matter experiments. There was a fantastic experimentalist there, Peter Eklund.
Yes, very, very famous. So optical properties of condensed matter.
Yes, he worked on carbon nanotubes.
Carbon nanotubes, yes.
Yeah. So I dabbled a little bit with doing experiments. Then I thought, okay, maybe I am. I did. I enjoyed doing experiments. He was also happy with my experimental skills, but then for various reasons I decided to do theory. So I decided to work with Professor Jainendra Jain in Penn State. We worked on quantum Hall effect. So after about 2 years of staying at Penn State, I started my PhD finally after 2 years. And then,
wow, fabulous. To the listeners, I should mention that Professor Jainendra Jain is one of the authorities on fractional quantum Hall effect, and Srijit has collaborated with him for a long period, right?
Yes, right.
We'll come to some particular questions what you have addressed with him, and he is also kind of associated with various Indian institutions, including IISER Pune. We had him as a visiting professor here at some point of time. So Srijit, tell us a little bit about before going into the research problem itself, I want to pick your brain on this mindset of getting into a mode of theoretical physics, especially condensed matter theoretical physics, which requires you to take input from systems which are in the real world. I mean, it's real in the world, real world. I mean to say, laboratory situations which can actually be even observed to a large extent. Of course, there are certain abstract phenomena which you may have to visualize and do things, and also bring abstraction from a mathematics viewpoint. What is the kind of foundation which you were trying to lay for yourself? This is actually, of course, a benefit of hindsight because you can now look back and think about it. What is the kind of training or some kind of preparation you had to do to really get in?
Yeah, that's an interesting question because I have jumped from many topics to many other topics over my life. But even when I switched from mechanical engineering to physics, I actually did not have much difficulty because I was doing GR and I could learn things from math books or textbooks. There were plenty of excellent GR books, and quantum mechanics. Also, you can sort of learn if you know linear algebra. You can learn most of quantum mechanics without a lot of and with a little bit of imagination. But moving from GR to condensed matter was very difficult. Condensed matter physics is not like any of the other topics. You need a lot of experience. Not everything is proved in textbooks. Even if you read papers, 90% of the things are not provable. A lot of things are in the collective intelligence of the people, and you have to be with them, sort of learn from them, and you need a lot of experience to be able to do it. So when I jumped into condensed matter physics in my third year, I actually struggled a little bit to figure out why we are doing what we are doing. But so it took me a long time to be able to produce something new. Of course, when you're doing a PhD, there might be, the PhD advisor, PI might have some immediate problem in mind, so you work on it. But to appreciate why you're doing that and why some problem is interesting or some things are done the way it is done, understanding that took a long time. And these are all issues at the level of understanding or abstract modeling. Then comes the issue of being able to connect with experiments. That took me a long time, but it is something that came out of reading a lot of papers and, more importantly, talking to a lot of people. Not something that I learned from textbooks. So training is actually a little more important, or who you discuss with is a little more important in condensed matter physics as opposed to the other things I've tried. So
yeah, because I've also observed, having also interacted with many of the other colleagues who are working on condensed matter physics, especially from theoretical viewpoint, they will have to interact with a lot of people, not only, of course, fellow theoreticians, but also with a lot of people, including chemists, for example. In fact, I have seen fabulous collaborations between material chemists and quantum condensed matter physicists. Like Umesh Wagmare is one of the examples which comes to my mind, and there are so many people who have done this very effectively. This also is very interestingly kind of connected to sociology, right? Because if you look at high energy physics, there again, the interaction between, let's say, theoreticians is very strong. If you're working on, let's say, a high energy theory, phenomenology, of course, they will actually have interaction with experimentalists. And they also are a very big group of people who actually are interested in certain set of problems. Whereas in condensed matter, you may have to spill over into disciplines beyond physics many a times. Whereas in high energy physics, maybe mathematics is one thing you will surely have to interface with. given your experience, how has it been interacting with people from various different backgrounds?
Um, th- uh, yeah, I don't want to comment on high energy physics because I don't do that, and it may be, my mental picture might be a misrepresentation of the actual truth. But my experience has been that, yeah, especially when you work on many body theory, even at the theory level, there are a lot of limitations. Right? Questions can very easily get intractable. So then you have to find directions in which you can make some progress and sort of chip away at problems in directions that are tractable. In a similar sense, when you try to talk to experimentalists, I have to admit that I'm not a person who does extensive collaborative work with experimentalists, but I do work with a few experimentalists. There are a lot of limitations. For instance, when I do theory, I can say, when I do computational theory, I can say, oh, I measure this, I measure entropy, I measure this, I calculate the spectrum and those kind of things. Most of these things are not possible in the experiment. So figuring out what's possible in the experiment takes a lot of it's again not something that you can read from a textbook. You have to talk to people, and therefore you need to have people around who you can talk to. And the limitations in the experiments could be actual physical limitations. It could be limitations in the available equipment, available samples. It could be just the difficult time scale of doing things. So those are things that I've learned by talking to experimentalists, and I mean those are, and also you talked about talking to different people. So the area is so vast that what even an experimentalist roughly working in the same field knows, or the way they perceive the physics can be different from the way I think about it. So you have to put some effort to connect to that way of thinking about things. Yeah. So yeah, maybe it's different for different people, but to me it comes only from trying and failing many times. Yeah. So.
Very interesting. So, how was it in Penn State, especially the condensed matter group in which you work? I have also I also had a conversation with Shiv Kumar Jolan, who was also from the same group where you work. Of course, he has taken a very different route altogether, and he is now a social scientist. And you actually have continued to work on very interesting problems, similar lines. Just paint us a picture about the kind of questions you were interested in then, and then we'll take the questions from there.
So I worked on what is called quantum Hall effect, and in the 2.5 years I worked on these at Penn State. I mostly worked on purely computational aspects of it. So there wasn't enough room. As I said, it takes a long time to be able to appreciate the things and try to, going to connect to experiments is further from that. So I mostly worked on developing techniques to, these are quantum many-body problems, and traditional perturbation theory that is applied in many other aspects of quantum many-body problems, that doesn't work. So you have to sort of invent techniques almost every time you come up with a new problem. So my efforts were mostly in trying to devise techniques to be able to calculate certain properties of quantum Hall systems from a theoretical point of view. For instance, understanding what are the quantum Hall systems have essentially some kind of correlated phases that appear when you take highly clean 2D electron systems in high magnetic field and low temperatures. It seems like an obscure thing to do, but the nice thing is that you see enormously rich set of physics, and these physics arise from highly correlated set of electronic states. But from the experiments, you can only see that there are these states, but you don't know what is inside them. And there are we have some guesses as to what happens. Surprisingly good guesses. And part of the task is to be able to verify that these guesses are correct. And I think most of my PhD years were spent in finding ways to do that. These are states with very strange correlations. So you had to find some way to do calculations with them. And yeah, I spent, I think, almost all the time trying to find out ways to do either computational or some semi-analytic way of doing calculations with them. Going beyond these specific calculations, going into understanding a broader picture of quantum Hall effect and being able to work with experiments, that happened only much later after I started doing my postdoc, or even after I came to ICER.
Yeah. So you did have a very good kind of foundation during that time, right? Because Jainendra, of course, is an authority in that area and also has done some very interesting work, which has also connection to experiments, right? Yes. Because even in the recent times when these so-called graviton-like modes which have emerged, there is some kind of a contribution from his theory too, right?
Yes.
Yeah.
So the nice thing here, I mean, phases of matter is something that has been studied for a long time and for a long time in condensed matter physics. So traditionally, these phases of matter were seen as some manifestation of the symmetries in the system. But, about 3-4 decades ago, it was realized that, okay, you could have phases of matter which arise from some kind of topology of the underlying electrons' behavior. So, I mean, it is an idea that came out of experiments that were done in quantum Hall systems. But the nice thing is that in quantum Hall systems, you can, these have been predicted in other spin systems as well, but quantum Hall systems, which essentially are properties of, are states that arise in electronic systems, they are experimentally observable. And what I find a bit amazing, surprising, is that though these are arising from strongly interacting electrons, which typically means that they're very difficult, intractable systems, in the specific case of quantum Hall systems, they are sort of tractable using some techniques that my PhD advisor developed. These are beyond techniques. This gives you an effective picture. Earlier, you were telling me about emergence. The physics in quantum Hall system arises from certain emergent particles called composite fermions, and you can see many experimental implications of the existence of these composite fermions, and you can explain many of the observed experiments using composite fermions. What is cool is that though this on the face sounds like an extremely intractable problem of interacting electrons, because of this idea of composite fermions turn out to be highly tractable. Still difficult, but there is a way to attack the
problem. Fascinating. So this also led you to newer ventures in a different continent post PhD.
Yes.
So tell us about that kind of transition.
Yeah. So after I finished my PhD, I continued to work a little bit on quantum Hall effect in the immediate couple of years after that. But I moved to Sweden to do my first postdoc in Stockholm, in a place called Nordita. So there, I also I had a senior colleague, Stephen Powell. He got me interested in statistical mechanics. So even though it was a problem, he was interested in the statistical mechanical aspects of the problem that he had in mind. The problem is essentially that of, I would say, domino tiling, but statistical mechanical aspects of domino tiling. To define a statistical mechanical problem, you need some energy scale. So there is some energy scale that you can define on top of the domino tiling structure. And my interest was to find algorithms that can do calculations with these configurations of dominoes and be able to do Monte Carlo calculations. It is a little difficult, okay, for those who know, you learn some kind of Monte Carlo method when you do simulate Ising model in some computational physics course. But there, the nice thing is that you can flip spins individually. You can change the degree of freedom locally on a site. But if you think of how you can look up what domino tiling problem is, it turns out that you cannot locally change anything. It's like one of these games where you have highly constrained set of degrees of freedom. You cannot locally change something. If you have to change something here, you have to change something there. So you cannot easily change the configuration of a system by just locally flipping something. You need to do something non-local, and that comes with some difficulties. And what I found interesting was to find clever ways to do these Monte Carlo moves, and that's what I did that's one of the things I did during my postdoc work, to basically find clever ways to do Monte Carlo on to solve problems in statistical mechanics of these are called dimers, but or domino tiling problems. Basically constrained problems where you may want to study some statistical mechanical aspects of it. Now, it is not a pure abstract problem. There is some connections to spin systems, but yeah. So this is what I worked on, basically finding ways to do Monte Carlo in constrained classical systems. So that was during my first postdoc. When I went to my second postdoc, in PKS in Dresden, I continued to work on quantum Hall systems. I continued to work on dimer model with Stephen Powell. And then I also worked on a few problems in quantum spin systems in cation models. And also at that time, there was a lot of interest in quantum many-body dynamics. So I started working on quantum many-body dynamics, especially what are called periodically driven systems. These are basically, traditionally people in condensed matter physics study things that are very close to equilibrium or slightly perturbed, things that are in equilibrium or things that are slightly perturbed away from equilibrium. Around the time I was doing my second postdoc, there were, in the community, there was a lot of interest in trying to understand what happens if you drive systems far away from equilibrium, especially quantum systems. In classical systems, there has been a lot of work for a long time, but in quantum systems, how do you deal with it? How do you think about it? So some of the interesting work in this direction was done at PKS, where I was joining as a postdoc. So I also started working on that. I have continued to work on all of these topics even now. Yeah.
Fabulous, fabulous. So one of the things I want to kind of explore a little bit more is the ability to pick a problem, because this is something which is universally important when you do research. The quality of the question, what you ask, depends very much on the kind of exposure you have to the area.
Yes.
What is the way you go about kind of exploring
A
problems?
lot of things that go into it. Some of the surprisingly, a good number of them are sociological, unfortunately. So
Unfortunately.
there are interesting problems which are, if there are problems that are very interesting and that has been around for a long time, then it's probably very difficult. That's not something I would give to a graduate student. So I do, quantum Hall effect is one such area where there are a lot of interesting problems, and I have been working on some subset of them, and they're typically very difficult, and it involves knowing the literature from a from several decades. Somehow I found that students find it difficult. So I generally, on quantum Hall systems, I do work on my own or with my collaborators. With students, I try to pick problems which, so because I have to train students, I do pick problems that are somewhat of contemporary interest and which have some set of low-hanging fruits, or some set of things, some set of open questions which doesn't require, which doesn't require them to spend several years just reading the literature. So that is one consideration when picking problems. Another consideration, unfortunately, is that most of the activity happens in the West in condensed matter physics. There are various reasons. But what happens is that when you sit here and try to learn about things just from arXiv, the ePrint repository, you are at a disadvantage because by the time something is on arXiv, probably 100 people have already thought about it, and the field is probably already saturated. So what happens is that over time, if you try to stay away from working on those kind of problems, you slowly go out of sync with the larger community in the world. So sometimes, unfortunately, I have to pick problems which may not be terribly interesting, but it allows you to keep track of what is happening in the literature. Maybe take a slightly tangential problem that sort of syncs with the new developments, but which allows me to think about them on my own. So there are various kinds of problems that you work on. Some things which are long-standing problems, which I've been working on for a very long time, for which I have some unique set of technical skills that I can employ. And then there are other problems that I pick depending on the interests of the students. Then there are other problems that I pick for these reasons, so that I keep up with the progress around the world. So, it's a mix of these.
Because see, this is part of the reason why I do this podcast is also to kind of get an overview of the intellectual history of the person who actually has been working on certain problems. This is more so important to chart out kind of explorations which an individual takes, and this exploration is generally in sync with a lot of other things, right? It need not be only driven by the person's interest.
Yeah.
A lot of things, as you mentioned, sociology also plays a critical role. Yeah. In your experience of having worked in now 3 different places, where US, Europe, and now in India, how has this kind of experience been? What are the kind of lessons what you've got having worked in these 3 places? There are, of course, very different ways in which people function in each country.
I think work culture is different. There's access to a lot of resources in the West. When I say resources, I'm not just talking about financial or equipment-related resources. It's also about access to experts with complementary research skills, complementary skills. When you're in India, sometimes you work on a problem and you need expertise in a slightly different area. You need to discuss with someone with slightly different expertise, and you find that there is nobody in the 1,000 or 2,000, 3,000 mile radius who has any complementary expertise. So sometimes you end up just sitting and figuring it out on your own. So it takes a long time to figure things out. On the other hand, this would have taken 10 minutes of a phone call to a colleague in another place. That makes a huge difference. Now,
but it's still feasible in a way because nowadays the technology is there.
Yeah, but it doesn't work as well when the person you're talking to is not in close contact.
Yeah, you're
It works to some extent, but nothing can take the place of having one-on-one interaction, discussing on a board. So I think that is a major disadvantage. Then, especially for a condensed matter physicist, there is the obvious disadvantage that the amount of experimental activity in India is much less. That means that so when there is a new development in Princeton, in some experiment, that information goes to their colleagues in the US, not to anyone in India.
Yeah.
And by the time you hear about it, 10 papers are probably already published on that. So, and same things happen in Europe as well.
This is actually a very important thing because it also determines the choice of the question.
Yeah.
As you clearly mentioned, either you have to really be in sync with that community which is spatially separated.
Yeah, that's a little stressful also.
Yeah, or you do something totally on your own.
Then you get to, sometimes you end up working on tangential problems because
absolutely.
The community is small if you try to work on orthogonal problems to the West.
True. It's actually an intellectual challenge for people like us, more so across the global south, so to speak.
Yeah.
But it also brings
I have to say that this is especially bad for condensed matter physics because it's closely related to experiments as opposed to some of the other fields where the world is flatter. In condensed matter physics, unfortunately, the world is not flat.
True. In fact, that's probably one of the advantages of high energy physics because the community is so international and tightly knit. Their exchange of information, if not ideas, are much faster maybe.
There is also the advantage of somewhat of a common language of quantum field theory. Condensed matter physics is way too complex to have a common language in which people with slightly different background can communicate. It takes a lot more effort, at least.
Fabulous. So give us a gist of the kind of questions you are now interested in.
So I work on. So I've been continuing to work on quantum Hall systems. Here, there are various experiments that are related to what are called anionic statistics. So understanding what that means and how it manifests and what are realistically measurable is one set of questions that I'm interested in. What anionic statistics means in the gist is that these are purported particles which behave neither like bosons or fermions. And it has been predicted, and there is enough somewhat convincing theoretical evidence that they exist, but when you take into consideration physical, experimentally measurable quantities, it turns out that it may not be as easy to observe as people thought. So I'm trying to understand what that means, and if there are ways to see indirect evidences of these kind of particles. That's one set of questions. And broadly, I'm working on understanding correlations in newer kinds of fractional quantum Hall systems, effect of certain experimental artifacts, in or experimental features in the actual experimentally realized quantum Hall systems. It could be that these experiments are realized in somewhat dirty, somewhat dirty 2D electron gases. Ideally, they should be done on some. Okay, and I'm basically looking at how the disorder in the sample affects the physics of fractional quantum Hall systems. I am working with some experimentalists on related questions. I'm also interested of late in using ideas of machine learning in quantum many-body systems. There are various aspects to it. One is to understand or try to see if any of the previously difficult problems in quantum many-body theory can be solved, or at least the solution can be improved using techniques of neural networks. So one of my PhD students working on it. Another area I'm working on it is something to do with using what are called tensor network states to study quantum dynamics. It's a bit technical, but roughly the idea is to find ways of using properties of quantum entanglement to find optimal ways to represent quantum dynamics. And using them to study non-equilibrium dynamics of interacting systems. Another direction I've been recently working on is to sort of use, again, ideas from neural networks or learning algorithms to sort of understand outputs from quantum computers. This is something that I've been working for about 6 months, but anyway, that's so a mix of things, but mostly related to understanding quantum many-body interacting systems, either in quantum Hall systems or quantum computers or quantum spin systems or quantum dynamics, but trying to use as many available techniques as there are to be able to find ways to understand some properties of these quantum many-body systems.
Fabulous, fabulous. So this is actually a part of the Emergence series, what we are kind of discussing on this particular podcast. So I'm hoping that we will revisit some of these things periodically at some point of time. And I also want to actually mention that I've had very nice kind of conversations and discussion with you, also related to some of your interest in slightly more applied problems, where you were looking at some devices, 2D devices and other things.
So I'm working on transport measurements in quantum Hall system and trying to understand realistic effects of confinement potential. So these are electrons that are confined to 2 dimensions, but 2 dimensions doesn't mean an infinite 2D plane. It actually is something that is confined in sort of 1 millimeter cross 1 millimeter region, or probably even smaller. That means that there are boundary effects, which has very strange counterintuitive features that on already some set of counterintuitive states of matter. So I have some collaborators who can actually do some of these measurements, and I'm trying to understand what they are finding. They sort of look like what we expect, but there are small deviations which contain physics that has to be understood. And then I'm also working on with some physicists. I mean, these experiments are done in Saha Institute. I'm also working on some other problems related to phase transitions between these phases of matter. And these phase transitions have something closely related to the physics of percolation that people study in statistical mechanics. And so these are fractional quantum Hall or quantum Hall samples. As you change the parameters of the sample, it goes from one phase of quantum Hall state to another phase of the quantum Hall state. I didn't explain what they are, but there are some phases of matter. But the transition has something intimately to do with disorder and how electrons percolate through this disordered system. And that brings an amazingly rich set of physics, and it brings in ideas from an amazingly wide range of ideas in physics, percolation, quantum tunneling, interactions, composite fermions, and all sorts of things. And what we are trying to understand is is whether what we are seeing in the experiment is what we are thinking from a theoretical perspective. So that's some set of experiments that are being done in IISc. Those are the two experimental ideas that are currently in my mind. Yeah, so.
Fabulous, Srijit. I wish you all the best for all the intellectual ventures and also the mentorship of the students and other related academic activities. So hopefully we will talk about many interesting aspects of quantum condensed matter in the coming years. Thank you very much. This is Pratidhwani, where we try to humanize science with the one and only Srijit DJ.